NASA has mandated that vehicles like drones, rovers, and electric cars will be equipped with high-quality cameras that live stream their entire mission back to Earth for everyone in the world to see. Not recorded, not delayed, but live. Every movement, every discovery, happening on the surface of another world. That sets us up for Phase 2, the transition into building a moon base. This plays out from 2029 to 2032. It involves 27 launches and 24 landings, and includes the first infrastructure for permanent habitation modules. This is where exploration starts, turning into something much bigger. The first real step toward humans living beyond Earth. In March 2026, NASA revealed an ambitious new plan for the future of American space exploration. On the surface, it looks like a blueprint for building a permanent presence on the moon. But the more important story is something deeper. NASA itself has changed into something the world hasn't seen in decades. And the reason for this shift goes far beyond new leadership. A new kind of competition is unfolding, one that will define who controls the next frontier of space. The old NASA was not built to win that race, but this new version is, and this is how it begins. When NASA leadership stepped forward in 2026, the message was clear. As NASA Administrator Jared Isaacman described it, one word captured everything: ignition, a single moment that signals the start of something irreversible. Not just a mission, but a transformation. The old approach has been abandoned. In its place is a new direction built on one simple idea: set higher expectations, and actually meet them. For years, NASA tried to satisfy everyone, and in doing so, achieved very little. The result was billions of dollars spent, and years of progress quietly slipping away. But this shift isn't just about efficiency, it's about urgency, because now there is more at stake than time or money. A new kind of competition is unfolding. One that will decide who establishes the first permanent presence on the moon. And this is not the space race of the 1960s. Back then, the goal was symbolic: flags, footprints, a moment in history. But this time, the objective is entirely different. This time, the goal is to stay. And we've heard promises like this before, for decades. Bold visions have been announced, only to fade without execution. Because words alone mean nothing in space. Real progress demands something far more difficult: a plan that actually works. And for the first time since the Artemis program began, that plan finally exists: a detailed, step-by-step blueprint for building a permanent base on the moon. And it begins with a decision that seems almost backward. Artemis 3 will not land on the moon. Instead, it becomes a full-scale rehearsal in low Earth orbit. At first glance, this sounds like a step back, but in reality, it solves the biggest flaw in the original plan. Because the old approach required jumping directly from a single crude test flight to a complex moon landing, using an entirely separate and unproven system. The risk was enormous. So high, in fact, that the mission timeline kept slipping year after year. The new plan changes that completely. Instead of rushing forward, Artemis 3 will bring the Orion spacecraft and the lunar lander together in orbit, testing everything before committing to the surface. The crew will transfer into the lander and begin testing the systems that will determine whether humans can actually survive on the moon. Life support, communications, propulsion, and for the first time, the new lunar EVA suits may be tested inside the airlock. Doing all of this in low Earth orbit changes everything, because here, if something fails, you can fix it. And that difference alone can mean the difference between survival and catastrophe. We already understand Orion. It has been tested, refined, and proven. But the lander is still the unknown. For years, it was assumed to be a version of Starship adapted for the moon. But that assumption is no longer guaranteed, as NASA Administrator Jared Isaacman confirmed. Another competitor has returned to the race. Blue Origin, with its Blue Moon lander. One or both of these systems may be tested during Artemis 3, and which one flies forward depends on a single factor, not contracts, not promises, execution. This is the defining shift inside NASA. Even the biggest players are no longer guaranteed anything. Winning once does not mean winning again. The company that delivers first will be the one that returns humans to the moon. Artemis 3 is now targeting 2027, and from that moment on, the timeline accelerates dramatically. Once a lander is selected, it will have only months to complete an uncrewed moon landing test, and then rapidly finalize a flight-ready system for Artemis 4. That mission is scheduled for early 2028, and this is when humans return to the lunar surface, targeting the South Pole. But as Isaacman made clear, this is not about symbolic victories. To prove that point, NASA plans to land astronauts again within the same year. Artemis 5 will follow before the end of 2028, not once, but repeatedly, because this time the goal is not to arrive, it is to stay. It sounds overly ambitious, but this is exactly how NASA once operated in its golden era. After Apollo 11, the next landing came just 120 days later. And this is not just history, it's a signal. Because that same tempo is returning. From this point forward, the goal is clear. A crew landing on the moon every 6 months, not once, not occasionally, but as a system. And this is where the mission changes completely. The focus is no longer just reaching the moon. It's building something that stays there. That shift forces a new priority. Surface operations come first, which means the original plan for a lunar orbit station, the Gateway, is no longer the center of the strategy. But nothing has been wasted. Every piece of hardware designed for Gateway is now being redirected into something more immediate, the first moon base. Because in space, distance is cost, and building directly on the surface removes an entire layer of complexity. The construction of that base will take about 7 years, with a budget of $20 billion, and everything unfolds in 3 phases. Phase 1 begins now. Phase 1 runs from 2026 to 2028. The objective is simple, but critical: reliable access to the moon. That means high launch frequency. 25 missions in just 3 years, with 21 actual landings. Only 2 of those will carry astronauts. The rest are something else entirely. Experiments, systems, infrastructure. Because before you can live on the moon, you have to learn how it works. And one of the first problems to solve is energy. The moon has sunlight, but not in the way we need. The Artemis base will experience nearly 2 weeks of constant daylight, followed by another 2 weeks of complete darkness. No atmosphere, no heat retention. When the sun disappears, temperatures collapse to around negative 330 degrees Fahrenheit, and without power, nothing survives. During those long nights, temperatures collapse to nearly negative 330 degrees Fahrenheit, and without a constant heat source, every system on the surface begins to fail. Metal contracts, batteries drain, electronics shut down, and once they freeze, they often don't come back. On the moon, cold is not just a condition, it's a shutdown. To solve this, NASA is turning to a technology that has already survived deep space for decades: radioisotope thermal generators. Instead of generating large amounts of electricity, these systems produce a steady flow of heat through the natural decay of radioactive material. That heat can be captured and used to keep critical systems alive through the long lunar night. And those systems are about to become far more advanced than anything we've used before. Because NASA is introducing an entirely new way to explore the moon: rocket-powered drones. The concept is called Moonfall, inspired by the Ingenuity helicopter on Mars, but redesigned for a world with no atmosphere. Instead of spinning blades, these drones use small rocket thrusters to hop across the surface. Each jump lasts around 150 seconds and can travel up to about 31 miles in a single leap. On a world with 1/6 of Earth's gravity, that kind of movement becomes possible. They will be sent into places humans cannot safely reach: mountain peaks, crater edges, regions where a single mistake could end a mission. And for the first time, exploration is no longer limited by wheels or even terrain. At the same time, NASA will deploy one of its most important surface missions, the Viper rover, a vehicle roughly the size of a golf cart, already built and tested, waiting for years for its chance to launch. In 2027, that moment finally arrives, delivered by a Blue Origin lander. Viper will begin a detailed survey of the lunar South Pole. But it's not just looking at the surface, it's searching for something hidden: water ice, locked inside permanently shadowed craters, places where sunlight hasn't reached for billions of years, along with hydrogen, oxygen, and rare materials that could support future operations. This is not exploration. This is prospecting. Because in the next phase, knowing where these resources are will determine where humans can actually live. And Viper won't be alone. It will be joined by a new generation of lunar vehicles, some driven by astronauts, others operating entirely on their own, each capable of traveling up to about 560 miles across the lunar surface. And these vehicles won't just explore. They'll work, moving equipment, leveling terrain, preparing the surface for construction. Because before you can build a base on the moon, you have to reshape the ground beneath it. Above them, a new network of lunar satellites will orbit continuously, enabling real-time communication from anywhere on the surface back to Earth, with data speeds reaching around 500 megabytes per second. They will also provide a continuous view of the entire lunar surface, and for the first time, this won't just be data for scientists. NASA has made a deliberate decision. Every major system, the drones, the rovers, the transport vehicles, will be equipped with high-quality cameras, streaming their missions live back to Earth. This isn't just exploration anymore, it's a shared experience. And that leads directly into Phase 2. The transition from exploration to construction. This phase runs from 2029 to 2032 with 27 launches and 24 landings. And for the first time, the infrastructure for permanent human presence begins to take shape. 6 new rovers will be deployed. But these are no longer just tools for discovery. This is where the work truly begins. Excavation machines capable of moving rock, leveling ground, and carving trenches for power lines and pipelines. But building on the moon is nothing like building on Earth. The dust is sharp, abrasive, almost like microscopic glass. Every movement wears equipment down. This isn't construction. It's survival engineering. One of the most advanced systems in this phase will be a pressurized mobile habitat, developed by the Japanese Space Agency in partnership with Toyota. Weighing around 33,000 pounds, this vehicle is designed to function as a fully mobile living space. Inside, astronauts won't need bulky suits. They can operate in normal clothing, traveling slowly across the surface at about 2 miles per hour, for days at a time. It's expected to last for 10 years and operate for up to 150 hours in complete darkness. Because on the moon, exploration doesn't stop when the sun goes down. It just becomes more dangerous. Phase 2 demands more power than anything before it, and that power comes from 2 sources. The first is solar. Panels mounted on tall structures, rising above the surface to capture as much sunlight as possible, feeding into large battery systems designed to store energy through the long lunar night. But solar alone is not enough. Because the moon is not a stable environment. Sunlight disappears for weeks at a time, dust settles, efficiency drops, so NASA adds a second layer: nuclear fission. Not just for heat, but for continuous, reliable power. Small reactors capable of generating steady electricity, supplying multiple systems at once, because without power, nothing survives. By the end of Phase 2, the foundation is complete. Systems are in place. Infrastructure is ready. And for the first time, the moon is no longer a place we visit. It becomes a place we can stay. Phase 3 is where everything changes. Beginning in 2033, humans don't just arrive on the moon, they move in. NASA plans for a rotating crew of 4 astronauts, living on the surface for up to 28 days at a time, not in a temporary lander, but inside connected habitat modules, forming a permanent base. These modules will be powered by their own nuclear systems and supplied with around 17,600 pounds of food, water, and air every month. But even that is not sustainable long-term, which is why the next step is critical: using the moon itself. This is called in situ resource utilization, extracting materials directly from the environment. Water locked inside deep, shadowed craters can be harvested and split into oxygen to breathe, and hydrogen to use as rocket fuel. In that moment, the moon stops being a destination and becomes a launch platform. And then comes the final step: building with what's already there. Lunar dust, rich in silica, can be melted and transformed into a form of concrete. Using advanced 3D printing, NASA can begin constructing permanent structures directly on the surface, not delivered from Earth, but created on the moon itself. If all of this sounds impossible, that's because it almost is. NASA has openly admitted that what they are attempting pushes the limits of what we can do today. But that's the point. This isn't being done because it's easy. It's being done because it's necessary. And they are not alone. Other nations are moving forward with the same level of ambition. These are the real stakes of the new space race. And in this environment, good enough is no longer enough. But there's something even more important than winning. Because the true objective of Artemis is not just to build a base on the moon. It's to prove that something far larger is possible. Because once humanity learns how to live on another world, everything changes. The moon is not the end goal. It never was. It's the first step towards something much bigger. A system that allows us to move beyond a single planet and become a multi-world species. And if that future is going to happen, it won't come from ideas alone. It will come from action. From people willing to build what has never existed before. So the question is simple. Not whether this can be done, but whether we're ready to do it. If you want to explore what comes next beyond the moon, stay curious, stay critical, and follow the journey as it unfolds.